Hello guys, good day. I'm excited to welcome you to another video today. So today we are going to be looking at something very exciting. We are going to be considering an atom. An atom is a very important area in chemistry that if it is well understood, then every other part of chemistry can also be understood, because chemistry boils down to the smallest detail. And if you talk about the smallest detail in every object, it is the atom. The atom is the smallest you can go in every object. Okay, so an atom by definition is defined as the smallest and indivisible part of an element. Indivisible part of an element. So these are the two keywords when you define an atom. So an atom is mostly represented with a circle, even though in the real sense, with a circle like this, even though in the real sense it's not exactly the way it's being represented. So there are some other features that are included, but are not going to be shown in this. This is just for the purpose of illustration. So let's say this is an atom now, okay? Let's call it the atom of carbon. So our carbon has an atomic number of 6 and mass number of 12. So let's say this is an atom of carbon. So an atom basically is made up of 3 vital components. We have the first one, we have the electrons. Then we have the protons. Then thirdly, we have the neutrons. So these are the 3 components of an atom, and each of them have their unique charges. So for the electron is always negatively charged. Okay, let me use this red. Negatively charged. The proton is positively charged, while the neutron is neutral. That is, it is neither positive nor negative. Alright, so these are the 3 components of an atom. So if this were to be an atom now, so the electrons are found outside the nucleus. This is called the nucleus. You find the proton and the neutrons are found in the nucleus. So this is the nucleus of the atom. This ball, the one with the thick line. So you find the electrons outside the nucleus. So you find this one in the shell. Finding the shell or the orbitals. Shell and orbital are not the same thing, but that is not the purpose of this video. So subsequent videos I'm going to do justice to electrons, but the purpose of this video is to look at the nucleus of the atom. Mainly we are going to look at the nucleus of the atom. So but we are still going to talk a little about the electrons. So if this were to be the atom of carbon, so like we said, the carbon has 6 protons. So, and also for every atom, the number of protons and electrons are always the same. They are always the same number, same amount. And the reason is because an atom is always neutral. It does not possess any charge. Because if the number of electrons were to be more than the numbers of protons, so that means it's going to be negatively charged. If the number of protons were to be more than the number of electrons, the atom is going to be positively charged. So, and that is when the atoms go into chemical reactions. But we are not looking at chemical reactions in this video. So we are going to be looking at atoms that have equal number of protons and electrons. So if this were to be an atom, in the shell you have, for carbon atom, let's say you have 6 electrons. So let's use black to represent that. So these are the electrons: 1, 2, 3, 4, 5, 6. And moreover, this is not the way the electrons are being arranged in the real sense of it, but just for the purpose of just to pass the message across. So let's just use this method to represent it. There is what we call electronic configuration, and that is what tells us the way electrons are arranged. But that is not the purpose of this video, like I've been saying. So we are not going to bother ourselves with that. So then in the nucleus, we have 6 protons. So these are the 6 protons. 1, 2, 3, 4, 5, 6. Okay. All right. Then we also have being normally the number of neutrons is not indicated for when you check your periodic table, but you can always get the number of neutrons by just subtracting 12 minus 6. So because the number of protons and the neutrons is what you call the mass number. This 12 is the mass number. The number of protons is the atomic number. So if you know the number of protons to be 6, you just simply subtract it from the mass number to give the number of neutrons. So this is the number of neutrons. So that means we also have 6 neutrons. So that is 1, 2, 3, 4, 5, 6. Okay. So the arrangement of the protons and the neutrons do not have any particular pattern. So they are just jumbled up together. So there is no any configuration for the protons and the neutrons. Okay. So this is how the nucleus of an atom looks like. All right. So now we want to look at something very important. We want to look at why is it that some atoms undergo radioactivity while others do not. So I want to look at why is it that some nucleus of atoms are stable while some are not stable. So for the atom of carbon, this nucleus is stable. That is, nothing leaves this nucleus or comes inside. And that's the reason why anytime you talk about chemical reactions, you don't talk about protons, you don't talk about neutrons. The only thing you make mention of is electrons. Electrons is only useful for chemical reactions. For chemical reactions. But when you talk about the protons and your neutrons, you are talking about nuclear reaction, that is radioactivity or nuclear reaction. So this video is not about radioactivity, but we want to look at the nucleus of an atom. But there's no way you can talk about the nucleus of an atom without making mention of radioactivity. Okay, so now there are 3 important forces that exist within an atom. Forces in an atom. Forces in an atom. 3 important forces that exist. Okay, let's draw another atom. Let's make it much bigger this time. Something much more bigger. So let's say this is let's use the atom of carbon. So let's make it much bigger this time. Okay, so this is the carbon atom. All right, very good. So we are only looking at the nucleus, not even the atom. So this, okay, let's just put a little, let's show the shell, something. So let's show the shell. But what you are focusing on is the nucleus. So, all right, so let's put the 6. 1, 2, 3, 4, 5, 6. And by the way, the atom is not, the nucleus of the atom is not, in short, it's less than 1% of the size of the whole atom. For instance, if this were to be an atom, the size of the nucleus is very tiny. It's less than 1%. It's even smaller than this. Then the other empty space, that's where you find your electrons. So in the real sense of it, the nucleus is much more smaller than the atom. So, but the reason why I'm representing it as big here is just to show the contents of the nucleus. So let me claim this. so that you don't take it as the real thing. The real sense of it is not as big. Okay, so we are talking about, we want to look at the forces in an atom. The number one force we want to look at is the nuclear force, the nuclear attraction. Nuclear attraction. So the nuclear attraction exists between shell, that is electrons, and proton. You find your protons in the nucleus. So in a nutshell, we can say the nuclear attraction exists between the shell and the nucleus, or between the electrons and the protons. So remember that you have your protons inside. 2, 3, 4, 5, 6. So that means you have this, the attraction it goes this way. So that is, you have an attraction, and so on and so on. So this force is what we call the nuclear attraction. Nuclear attraction. So that's the first force. So, but let's go to the one we are more interested in as far as this video is concerned. So the second force, that's what we call the electrostatic repulsion. Electrostatic or electrostatic repulsion, they mean the same thing. Electrostatic repulsion. Remember, according to the laws of electrostatics, that says that like charges repel, unlike charges they attract. So that applies here also. So electrostatic repulsion occurs between the protons in the nucleus of an atom. So that is, you have these forces, you have this pushing each other away, pushing each other apart. So this is the electrostatic repulsion. So exists between every proton in the nucleus, and they also exist. They push each other away. They are pushing each other apart. So this represents they are pushing each other apart. Okay, all right. So these are the electrostatic repulsion, and they exist between protons. And moreover, repulsion also exists between electrons. That's a different story entirely. So you talk about that when you look at the shape of your atom. So when you go into the geometry of an atom, but we are not going into that in this video. So protons of atom. Then the third force is what we call the strong force. The strong force. There's a reason why it's called a strong force, because it is actually the strongest force known in the universe. It's the strongest force known in the universe. And the strong force is simply the force that exists between the protons to protons, between protons to neutrons. So this force exists between everything that is inside the nucleus of the atom. So that means let's use carbon. So we have 6 neutrons. 3, 4, 5. Let's put the last one where, okay, let's put it here. Let's put it here. Okay, let's put it here. 6. So that is, there's a force that exists between this and this. Sorry, let me close it. There's a force that exists between this. There's also a force that exists between this also. So you can see something that this looks like a contradiction. We say that the protons, they repel each other, but at the same time they still attract each other. But the force of repulsion, the force that pushes them apart, is much stronger than the force that attracts them. That is a strong force for protons to protons. And that is the reason why you need the other force from the protons to the neutrons. Let me say that again. The force that attracts, that pushes two protons apart from each other, is much stronger than the strong force that attracts the two protons together. And that is why you need the force, this other strong force to attract the protons with the neutron. So we already said that protons, the strong force is between the protons to protons and the neutrons. So, and that is what makes the nucleus of the atom stable. So it's this strong force that gives the atom stability, and that is why the atom is stable. The nucleus does not break apart. The nucleus only breaks apart when you come to nuclear fission, and that's when you talk about atomic nuclear bomb. So that's where you have the nuclear fission, breaking apart of the nucleus. So we also have the combining of the nucleus, joining together of the nucleus, which is the nuclear fusion. So when you break it apart, you have what you call fission. So, but that is not the purpose of this video. So, all right. So, but there is a limitation for the strong force. The strong force has a limitation. It has a limitation. Okay, let's look at the periodic table very quickly. Let's consider the periodic table. Watch out for subsequent videos. I'm going to make videos on the explanation on the periodic table. So, okay, but let's just look at let's just pick some elements from this table here. Let's pick carbon still. I don't know why I like carbon so much. Maybe it's because it's one of the most abundant, if not the most abundant element in nature. Okay, this is carbon. Oh, this down, this up. Okay, this is carbon, this 12, this 6. Okay, let's look at another element. Let's say uranium. So uranium is 238 and 92. Okay, so okay, let's use a new page for that. So let's represent uranium in this case here now. So let's say this is the nucleus of uranium, and uranium has 238. Okay, 238 and 93. 238 and 93. Okay, that means there are 93 protons, while there are 238 minus 93 neutrons, which is equal to 139. Is it 139? No, it's not. Let me crunch my calculator. 238 minus 93. 238 minus 93. Sorry, it's 92. It's 92. It's 92. Sorry. So this is 92. So 238 minus 92. 238 minus 90. 2. So that's 146. We have 146 neutrons. Okay. All right. So 146 neutrons. So uranium has 146 neutrons and 92 protons. But for carbon has 6 protons, 6 neutrons. So we are still on the strong force. So the reason why for an element like uranium, checking the periodic table, these are called the heavy elements. So these are the elements that undergo radioactive decay. That is, they are not stable. They are not stable. They can easily break apart. But remember, we've said that the nucleus of the atom can hardly break apart. But it does not occur for elements in this case, especially the actinide. The actinide, they are the one here. So they are not stable. So, but why are they not stable? So the reason is simply because we said that the strong force give them their stability. But for an element like an atom like uranium now, that has more neutrons. So what this simply means is that the nucleus is jam-packed more with neutrons than protons. So let's say we have our protons. These are protons. I'm not going to draw 92 protons. I'll just use a ratio to represent that. So then we have that means our neutrons are as almost twice of our protons. So that means they are jam-packed with more neutrons than protons. So this is it. Okay. Well, let me just leave it like that. All right. Let's stop here. All right. So what this simply means is that the strong force we said exists between the protons and neutrons. All right. There's something I left out here that I wanted to say the other time. Skipped my mind. So the strong force exists between very close proximity, close distance. The strong force only exists between the close distance. That is, when the protons and the neutrons, they are far apart, this strong force might go away. So and that makes the nucleus unstable. But when they are very close apart, then the force exists. But when they are far apart, the force is very negligible or it doesn't exist at all. So coming back to this now. So that means there's a strong force between this proton and the neutron. But at the same time, there's a strong force between this proton and the neutron. But the problem is that because the neutrons are more, so there's going to be a tendency that the strong force will not go round. There will not be an equal sharing of the strong forces. So that will make some of the neutrons to be loosed. So that means that the stability in the nucleus of the atom, that means that if you are to pair each proton with each neutron, because the numbers are not equal, so that means some of them will be unpaired. So and that makes the heavy elements, that makes them unstable. And that is the reason why if you check for the light elements, the protons and the neutrons are always 50%. 50% each. Almost, if not exactly. They are not always 50%, but sometimes you find maybe 51, 49, 52, but they are always very close. Whereas we have to find a percentage in this, you are going to discover that it's far less than 50%. And there's what we call neutron-proton ratio. So neutron-proton ratios for heavy elements that are not stable, they are mostly between 1.5 upward. So we find the proton-neutron ratio for neutron-proton ratio for uranium is going to be 146 divided by 92, which is going to be, let me crush my calculator, 146 divided by 92, that's 1.587. That's 1.587. Whereas in this case, 6/6, which is equal to 1. So that's the reason why heavy elements are unstable, while light elements are stable. So even elements as close as 1 point, the neutron proton ratio as close as 1.45 can be found to be unstable also. So it's just a matter of the protons and the neutrons. All right. So in the next video, in the subsequent video, we are going to talk more about the electrons. But this video is just to make you understand why the nucleus of the atom is the way it is. All right.